What is algorithm? An algorithm is a set of instructions or rules designed to solve a specific problem or perform a particular task. It is a step-by-step procedure that outlines the necessary actions to achieve a desired outcome. Algorithms are used in various fields, including computer science, mathematics, and everyday life. In this article, we will explore the concept of algorithms, their characteristics, and their applications. 1. Definition and purpose. An algorithm is a well-defined sequence of instructions or rules that outline how to solve a problem or accomplish a task. It provides a systematic approach to breaking down complex problems into smaller, more manageable steps. Algorithms are designed to be executed by machines or humans to produce a desired result efficiently and accurately. 2. Characteristics of algorithms. Algorithms possess several key characteristics. Input. An algorithm takes one or more inputs, which serve as the initial data or problem to be solved. Output. It produces one or more outputs, which represent the solution or result obtained from executing the algorithm. Clear and unambiguous. Algorithms are precise and leave no room for ambiguity. Each step must be well-defined and understandable. Finiteness. An algorithm must have a finite number of steps. It should terminate after a finite amount of time, producing the desired output. Effectiveness. Every step of the algorithm should be feasible and practical to execute, using available resources. Determinism. Algorithms produce the same output for the same input, ensuring consistency and predictability. Generality. Algorithms are designed to solve a particular problem or task in a general and applicable manner, not limited to specific instances. 3. Components of algorithms. Algorithms consist of several components. Control structures. Control structures, such as loops, conditionals, and branches, govern the flow of execution within an algorithm. Data structures. Algorithms utilize data structures, like arrays, lists, or trees, to store and manipulate data during the execution process. Operations and actions. Algorithms include various operations and actions, such as arithmetic calculations, comparisons, sorting, searching, or data manipulation. Termination conditions. Algorithms specify termination conditions or exit criteria to determine when the execution should stop. Error handling. Error handling mechanisms are incorporated to address exceptional or unexpected situations that may occur during execution. 4. Algorithmic complexity. Algorithmic complexity refers to the efficiency and resource requirements of an algorithm. It assesses factors like time complexity, how long an algorithm takes to execute, and space complexity, the amount of memory an algorithm requires. Efficient algorithms aim to minimize time and space complexity, enabling faster and more scalable solutions. 5. Applications of algorithms. Algorithms have extensive applications across various domains. Computer science and programming. Algorithms are fundamental to computer science, guiding the development of software, data analysis, artificial intelligence, and other computational tasks. Mathematics. Algorithms play a crucial role in solving mathematical problems, such as finding prime numbers, calculating Fibonacci sequences, or performing matrix operations. Search engines. Search engines utilize complex algorithms to retrieve and rank web pages based on their relevance to a user's query. Optimization. Algorithms help optimize processes and decision-making in fields like logistics, scheduling, resource allocation, and financial planning. Machine learning and AI. Machine learning algorithms enable computers to learn from data and make predictions or decisions without explicit programming. Cryptography. Algorithms are essential for encrypting and decrypting data, ensuring secure communication and protecting sensitive information. In conclusion, algorithms are systematic procedures that provide step-by-step instructions to solve problems and accomplish tasks. They are characterized by their clarity, determinism, finiteness, and effectiveness. Algorithms are utilized in various domains, from scientific research and mathematics to computer science, search engines, optimization, machine learning, and cryptography. They enable efficient problem-solving, decision-making, and data manipulation. Understanding algorithms and their applications is essential in fields that rely on computational processes, as they provide a structured approach to tackling complex problems and achieving desired outcomes. By analyzing inputs, applying logical operations, and producing outputs, algorithms serve as the backbone of many technological advancements and innovations that shape our modern world. 6. Algorithm design techniques. There are various techniques used in algorithm design to create efficient and effective solutions. Brute force. This technique involves trying all possible solutions to a problem, often through exhaustive search. While simple, it can be time-consuming and inefficient for large problem sizes. Divide and conquer. This technique breaks down a problem into smaller subproblems, solves them independently, and combines the solutions to solve the original problem. It often employs recursion to handle the subproblems. Greedy algorithms. Greedy algorithms make locally optimal choices at each step with the hope of achieving a global optimal solution. They prioritize immediate gains without considering future consequences. Dynamic programming. Dynamic programming involves breaking down a problem into overlapping subproblems and solving them only once, storing the solutions for future use. It eliminates redundant computations and improves efficiency. Backtracking. Backtracking is used to systematically explore all possible solutions by incrementally building a solution and undoing the choices that lead to dead ends. It is commonly used in solving constraint satisfaction problems. Randomized algorithms. Randomized algorithms use randomness, such as randomization or probabilistic choices, to achieve efficient and effective solutions. They are often used in situations where finding a deterministic solution is challenging. 7. Algorithm analysis. Analyzing the performance and efficiency of algorithms is crucial to understand their behavior and make informed decisions. Key aspects of algorithm analysis include time complexity. Time complexity measures the amount of time an algorithm takes to run as a function of the input size. It helps assess the efficiency of an algorithm and determine its scalability. Space complexity. Space complexity measures the amount of memory an algorithm requires as a function of the input size. It helps evaluate the memory efficiency and resource utilization of an algorithm. Big O notation. Big O notation is used to express the upper bound or worst-case performance of an algorithm. It provides a standardized way to compare and categorize algorithms based on their growth rates. Asymptotic analysis. Asymptotic analysis focuses on the behavior of algorithms as the input size approaches infinity. It helps identify dominant factors that determine an algorithm's efficiency. Best, worst, and average cases. Algorithms may have different performance characteristics depending on the input. Analyzing the best, worst, and average cases provides a more comprehensive understanding of an algorithm's behavior. 8. Algorithmic challenges and trade-offs. Developing algorithms often involves making trade-offs between different factors. Time versus space. Improving time complexity may require sacrificing space efficiency, and vice versa. Finding the right balance depends on the specific requirements and constraints of the problem. Accuracy versus speed. Some algorithms prioritize accuracy, providing precise results at the expense of longer computation time. Others prioritize speed, providing approximate or heuristic solutions quickly. Complexity versus readability. Highly complex algorithms may be efficient but difficult to understand and maintain. Striking a balance between complexity and readability is essential for code maintainability. Optimization versus generalization. Algorithms can be optimized for specific scenarios, but this may limit their applicability to broader contexts. Generalized algorithms sacrifice some optimization for versatility. 9. Ethical considerations. Algorithm design and implementation also raise ethical considerations. Bias and fairness. Algorithms can reflect biases present in the data used for training or design, leading to discriminatory outcomes. It is essential to address bias and ensure fairness in algorithmic decision-making. Privacy and security. Algorithms may handle sensitive information, requiring measures to protect user privacy and secure data from unauthorized access or misuse. Accountability and transparency. Algorithmic systems should be transparent and accountable. It is important to understand how decisions are made and provide explanations or recourse in cases of errors or biases. Algorithmic impact. Algorithms can have significant societal impacts, affecting areas such as employment, education, healthcare, and criminal justice. It is crucial to consider the potential consequences of algorithmic decision-making and ensure that it aligns with ethical principles. Human oversight. While algorithms can automate processes and improve efficiency, human oversight is essential to ensure that the outputs are reasonable, ethical, and align with human values. Humans should have the ability to intervene and make informed decisions when necessary. Algorithmic transparency and explainability. As algorithms play an increasingly prominent role in decision-making, there is a growing demand for transparency and explainability. Users should understand how algorithms work and be able to assess their impact. Bias mitigation. Efforts should be made to identify and mitigate biases in algorithms, both in the data used for training and in the design of the algorithms themselves. Regular monitoring and auditing can help address bias and promote fairness. User consent and control. Users should have control over their data and be able to provide informed consent for its use in algorithmic processes. Clear policies and mechanisms should be in place to ensure user autonomy and protect their rights. In conclusion, algorithms are fundamental tools used to solve problems and accomplish tasks in various domains. They provide a structured approach to problem solving, employing techniques like divide and conquer, dynamic programming, and greedy algorithms. Algorithm analysis allows us to understand their performance characteristics, while trade-offs and ethical considerations guide their design and implementation. As algorithms continue to shape our digital world, it is crucial to address ethical concerns, promote fairness and transparency, and ensure that algorithms serve the best interests of society. Thanks for watching.